So this is a typical FRQ on the AP Calculus exam, and I'm going to break it down to show how easy these questions can actually be. So before approaching these kinds of questions, the key word is to try and visualize as much as possible what they're actually asking. So you can see here when we begin, they say fish enter a lake at a rate. So we can immediately try to visualize this by drawing a lake. Assume this is some kind of lake, and fish are entering it, right? Modeled by the function e, given by e of t equals this. So we can associate the function e of t with entering the lake. And whenever they give you mathematical functions like this, it is extremely important to understand what the function represents. So what does e of t actually mean here? Well, you can see a key word here, rate. And in calculus, rate is a very important word. Rate is associated with rate of change, or the derivative, right? So e of t must be the derivative of something. And because they say fish enter the lake at a rate, then it must be the derivative of fish in a lake, right? Or something like that, right? So it's very important to not get confused and mistake e of t for something else. So if it helps, you can even write rate here to know that this is talking about the rate of change. Okay, and now they say fish leave the lake at a rate modeled by the function L given by L of t. So we can draw fish leaving the lake represented by L of t. And this is also the rate, right? Pay attention to the word rate there. Now, both E of t and L of t are measured in fish per hour. Okay, so that verifies our idea that these functions are talking about the rate, right? Fish per hour. And t is measured in hours. So we know that t is talking about time. These functions are functions of time. So now that we fully understand what the question is asking, we can visualize what is happening. Fish are entering the lake at this rate, or at some rate, and fish are leaving the lake at some rate. And this rate is different for different times, right? Maybe midnight is a different rate. During noon, it's another different rate, right? So now we can begin the actual questions. So they say, how many fish enter the lake over the 5-hour period from midnight to 5 a.m.? And to give your answer to the nearest whole number. So we can try and visualize what's happening here as well. So how many fish enter the lake? So that's important, right? What does it mean? What do they mean by that? To enter a lake. Well, the units you would use to express fish entering a lake would be just fish, right? The number of fish. So that's why you can't assume this is talking about E of t, because E of t is talking about the rate that fish enter the lake. This is talking about the number of fish, how many. Many is associated with the number, right? The quantity that fish enter the lake. For the number of fish that enter the lake. But we can think and realize that if you have a function that represents this, let's say, okay, some function, it's talking about the number of fish that enter the lake. Then the derivative of that function is the rate of change of fish that enter the lake, right? And that's E of t. E of t, fish enter the lake at a rate modeled by the function e, right? So E of t is actually the antiderivative of this function that says how many fish enter the lake, right? So we would just write the integral of E of t dt, right? And they say over this 5-hour period. So they give us this initial time and this final time. So that is a clue that maybe this is a definite integral from 0 to 5. And this is a calculator-based question. So they let you plug this into the calculator, where E of t is this function right here. And it turns out that it gives you 153.458. And if you round it to the nearest whole number, like they said, it's just 153. Fish. So that is your answer. And that would be part A. That would be all you need to do to get full credit for part A. So part B says, what is the average number of fish that leave the lake per hour over the 5-hour period from midnight to 5 a.m.? Okay, so now when we approach this question, we can continue to try and visualize what's happening. So when they say average number of fish that leave the lake per hour, what does that mean? Well, if you think about everything that you learn in calculus, something might appear in your mind, and that's that there's some kind of formula or maybe some kind of concept associated with the idea of average number, and that is given some function f of x. There's actually an average value, okay, over the interval a, b, right? There's an average y value in this interval, just like how you would take the mean of, a group of numbers, except now you have infinitely many numbers, and you take the mean of these infinitely many y values. What is the average of that? So for this particular function, it's like about that value right there. But how would you calculate this? Well, it's actually just the integral from a to b of f of x dx over b minus a. Just like that. So what is f of x then? Well, it would actually be L of t in this case. Why? Because what is the unit that they're talking about? The average number of fish that leave the lake per hour. Per hour. So per hour is talking about rate, right? L of t is measured in fish per hour. So that's why this is just f of x is just e of t here. dt. And b and a and b are just 0 and 5, right? 0, 5. 5 minus 0. And now you can kind of understand what's happening here. Let's say this is e of t now, right? So maybe this is t. There's this function e of t. It represents the rate of change of fish leaving a lake from this time from midnight, and now it's 5 a.m. What is this average y value? Well, you use this formula and you can plug this into the calculator, and you get 6.059 about. It's a good idea to usually round it to 3 decimal places. So 6.059. Alright, so part C says, at what time t, for t is from 0 to 8, is the greatest number of fish in the lake? And to justify your answer. So first, what are they asking? Right here, the greatest number of fish in the lake. Now, when we think about the greatest number, and we think about everything we know in calculus, what concept is associated with greatest number, right? Like just how we thought about average value, and what concept is associated with that. Well, it would be the absolute max, right? And what is the absolute max? It's over some interval for some function. What is the greatest value? The greatest y value in that function, right? And how would you find that? Well, you just take the derivative of the function and you set it equal to 0. And those those x values that allow the derivative of the function to equal 0 would be what you call critical points, right? And then you test out all those little critical points, and then you test the endpoints, and the greatest value would be the greatest value for that function, right? Over that interval. So let's do that. But first of all, we need to know when we're taking the derivative of a function and setting it equal to 0, what is that function in this case? Well, it isn't exactly E of t. It isn't exactly L of t either, right? E of t is talking about entering. L of t is talking about leaving. This is talking about the number of fish in the lake. So in is not really entering, right? It's not really the same thing. And this is not talking about the rate either. So really, what they're saying is, for this lake, E of t and L of t, they're happening at the same time. Fish are entering and leaving the lake at the same time. So any given moment in time, you have some number of fish. And this number is changing at any given moment in time, essentially. And we want to use a function that describes that. So let's call it f of t. Okay. Now, how are we going to describe this? Well, what if we wrote E of t minus L of t? Because maybe entering minus leaving gives some idea. But no, that's not really it. Why? Because you have to pay attention to the fact that these are talking about rate. Remember, this is not talking about rate. This is talking about the number of fish. So the units are just fish, right? So this is not exactly it. This is still in terms of fish per second. But we do know that all you have to do is take the antiderivative to go from the rate of change to just simply the number, right? So we could just say from 0 to some t value, right? dt. And let me do that, because these are still the same thing, okay? E of x, L of x, they're still the same thing as E of t and L of t. It's just that if you write an x here, or if you write a t here, it would make things confusing, because t is supposed to be your input. So you input t here, here, and here. That's not how the function works. The function is saying from 0 to some number, some time, from midnight to some time of the day. You're taking the integral from 0 to some time of the day for this function right here. So you can't plug the time into here either. These are just the functions. So that's why that's not confusing, or well, that is kind of confusing, but that's why, just to not make it confusing, that's why you don't put a t there. So, but they're still the same thing. This is still the same function, okay? So this would be our function, our universal function. And to find the greatest value of this function, we just take the derivative. And when you have a derivative and an integral, they cancel out, right? Okay, now we just set it equal to 0. And you will need a graphing calculator now, which is allowed in this case. E of t minus L of t, you just type this in minus this, but maybe surround this by parentheses, right? And that would be your function. And when you graph it, you would see all the x values, or in this case t, where the function equals 0. And those would be what you're trying to find. Those would be your critical points, right? So it turns out that those values are actually t equals negative 6.6, about negative 2.5, negative 4, and 6.204. Okay, right off the bat, we can eliminate some of these. Why? Because time cannot be negative. Okay, that's just, no, it's from 0 to some time. Okay, time cannot be negative. So we only have 1. But does that mean that this is the time in which we have the greatest number of fish in the lake? Well, no. Remember, we also have to consider the endpoints, right? So we also have to consider, if we make a graph here, t values and well, your output, the number of fish. We know one potential time is 6.024 or 6.204. Another time is the endpoint, so 0. And then t, what is t? They said it was 8. So okay, so let's test these out. All you're doing is you're just plugging in t into this function, because this function, remember, it's giving the number of fish into, right here, and seeing what we get. So if you plug in 6.204 into this right here, you will get 135.015. If you plug in 0, well, 0 to 0 is just 0, right? If you plug in 8, you get 80.92. Okay, so it's clear here that this is the maximum value, right? At time equals 6.204, the greatest number of fish occurs. It's 135 for this interval from 0 to 8. So we would just write, well, we actually circled it right there. So it'll just be this right here, 135.015. And then they say, justify your answer. So how do you justify it? Okay, by using this test, right, and saying, okay, by testing, well, testing all the testing the critical points and endpoints the one with the maximum value, the t value out of these with the maximum value would be the one with the greatest number of fish. And that is enough to justify your answer, right? Because this right here, this is a very clear process of what's happening. So I won't write it all out, but that's basically what you would say. Just, you don't have to go in depth by a lot, right? Like they understand what you're saying here when you say, oh, I'm testing critical points and endpoints, right? I'm trying to find this maximum value. So that would be part C. So part D says, is the rate of change in the number of fish in the lake increasing or decreasing at t equals 5? And to explain why. Okay, so now what are they asking? Is something increasing or decreasing? Or, yeah, increasing or decreasing. So what is increasing or decreasing exactly? What is it saying? The rate of change in the number of fish. Okay, so what is the rate of change in the number of fish in the lake? So you have these fish in the lake, and as time passes, what is the rate of change of that? So that's just, remember, f of t. It's just the derivative of f of t, right? The rate of change of the number of fish in the lake. F of t represents the number of fish in the lake. And if you remember, f of t is just the integral of e of t minus l of t, blah, 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 right? F prime of t is simple. It's just e of t minus l of t. So this is literally saying the rate of change in the number of fish in the lake. And it makes sense too. You have fish entering and leaving. So you subtract the fish leaving from the fish entering, and you get the net total rate of change in the number of fish in the lake. Okay, so let's say, and what are they asking? Is it increasing or decreasing? So let's say this is f prime of t, if we wanted to graph it, you know, just say maybe. It definitely wouldn't look like this, but just assume it looks something like that. This is f prime of t, let's say, and at this point is 5. So they're asking, at this point right here, is the function increasing or decreasing? Well, the way I drew it, it is decreasing, but you know, it could very well be, the function could be maybe going something like that or something. You know, this is just the way I drew it. But how do we figure out if a function is increasing or decreasing? So this is another big idea in calculus, just like the average rate, or the average value, just like the maximum value, right? What does this remind us of? If a function is increasing or decreasing, that's talking about the derivative, right? The instantaneous rate of change. If we have a function it's going this way, like this, and at this point, the slope right there is positive, so the function is effectively increasing at that point, right? It's doing this. The slope is negative at that point. Then the function is effectively decreasing, right? So how do we use that knowledge here? Well, we just take the derivative of this, right? And then plug in 5. Because we take the derivative of this, we know what we literally are doing is we will know the slope at 5. And we plug in 5, right? So let's do that. This would, yeah, you could say it's f prime of t, but that's really irrelevant now. We just want to know what this function is, the derivative of this function is. It's really e prime of t minus l prime of t, right? And you can plug this into the calculator. What you would get is, well, actually, you would have to set t equal 5 first, of course. You'll get a value, right? E prime of t, that's some function, and then minus L prime of t, which is the derivative of this function. You get that function. You plug in 5 for t. You get a value, and it turns out that value is negative 10.723. So remember, what does this mean? This is saying you have some function, it's f prime t, at this point right here, where this t equals 5, okay, the function, the slope, the instantaneous rate of change at that point, slope, it is negative 10.723. So it's slanted very steeply, right, downwards, right, like that. So what does this actually mean in this scenario? Well, it just means that the fish is decreasing and at a pretty high rate too, right? The rate of change. See, you can't ignore that. The rate of change and the number of fish in the lake is decreasing by a lot. So it's decreasing. The answer is decreasing because the slope is negative. And if you wanted to explain why, well, it's very simple. At this point, right? At this point, for maybe here, for f prime of t, or maybe it's more accurate, but really it's not a big deal. For this function e of t minus l of t, the slope, or the instantaneous rate of change, slope, is negative at t equals 5. That's it. Or you could say, and you could reword it and say, for e of t minus l of t, the derivative where t equals 5 is negative. Therefore, the slope is negative. Therefore, it's decreasing. So that would be part D. And that would be all you need to solve this FRQ. So you can see that solving these questions are not particularly overly complicated or anything like that. Most of these questions, they are really referring back to some fundamental concept. For example, the derivative and the function increasing and decreasing, how it's associated with the derivative, or how the average value is associated with some formula that you have to recall, or what is the absolute max? How do you find the absolute max, right? If you can visualize what's happening, it's very easy to, if you can visualize what's happening and you can remember those fundamental concepts, it's very easy to immediately know what to do, what formula to apply, or what the steps are. Okay? But the most important thing is to know why you are doing these steps. You cannot blindly go through these steps and just do it and get an answer and not even know how you got there. You have to know this thing, like the number of fish in the lake, how can you represent it using some concept in calculus? And the best way to do that is simply to just practice. Do as much FRQs as possible, and to continue to try and visualize what's happening, because that will give you a much better idea of how you can express this using some kind of, or certain aspects of this, using some kind of concept in calculus.